So today I'm going to tell you how mathematics help us get around these problems and not being able to use your naked eyes to see, but rather you need some other types of waves to detect these phenomena, right? And so essentially I'll tell you 4 short stories, right? So usually a colloquium you give a story, so instead I give you 4 short stories. And the first story is how we can use rays to tell us things, or to see things on a cosmic scale, right? So we're going to see how we can use gravitational waves to image the universe, right? On a geographic scale, we'll see how we can use seismic waves to help us see what is under the ground. And on a human scale, we'll see how things like X-ray can help us detect tumors or cancer. And on a subatomic scale, I'll show you how we can use various waves to help us detect quantum mechanical structures that we would not otherwise see using our eyes. All right, so that's the 4 short stories that I will tell you today. So we start with a story that was a long time ago in a galaxy far, far away. Right, so I wish to see now what is out there in that galaxy. So let us now pretend that we have these equipments or these instruments that we can shoot up into space, and then these instruments can somehow propagate gravitational waves, right? So we don't have these instruments yet, but let's suppose that we have them. And so we aim these instruments in the general direction of the galaxy, and then we shoot these gravitational waves. And because gravitational waves are nonlinear, when they collide like that, they're going to interact in a nonlinear way to actually send a wave coming back. So it's going to boomerang come back. And then, because it comes back to Earth, we can then make that detection, right? We can detect that ray coming back to us. So the question is, if I do this experiment many, many times, and I listen to a lot of these echoes that comes back, can I then reconstruct the structure of it, or the geometry of space-time, right? So it turns out the answer is yes. And this thought experiment was developed by Kurolev, Lasas, and Ullmann. And so whenever you talk about space-time, the most convenient way to talk about it is using something called a Lorentz of many things. And this is essentially what you do is you take space, which is these horizontal slices, and you take Cartesian product with time, which is the vertical component, right? So at each horizontal slice here, essentially you can think of it as a snapshot of what space looks like at that time. And the thing about when you draw things in this diagram is that nothing really stands still. So even though I'm here standing still, or I'm stationary, whatever that means, right, nevertheless, time is passing through me. So my trajectory in this space-time diagram is actually this vertical line right here. Yeah? So for example, similarly to this classroom, right, this classroom is an open set in space, and the trajectory of this classroom in space-time is then a cylinder going upwards, right? So that's the way to think about these space-time diagrams. And so this thought experiment was by Kurolev, Lasas, and Ullmann. They considered a vicinity of the Earth, right? So here's the vicinity of the Earth, which is an open set in the universe. And as I said earlier, it makes a space-time cylinder as time progresses, right? So they say, well, suppose then I put some sources in the vicinity of the Earth, and then I shoot these sources so that they would actually propagate these waves, and these waves would satisfy this wave equation, this nonlinear wave equation with a nonlinear term. Right, and of course I would like to be able to observe these waves everywhere in the universe, but I cannot because I'm here stuck on Earth, and the most observation I can make is in the vicinity of the Earth, in this green part. Right, so the question is then, if I were to place various sources in the vicinity of the Earth, and then observe the wave that propagates out of them in the vicinity of the Earth, can I then reconstruct the space-time geometry of the universe from these observations? And the answer is yes, right? And I will tell you how they go about doing this, or at least give you a general idea of how they go about doing this. So first of all, I would like to say that this problem is challenging because you are given analytical information, which is solution of a wave equation, right? So, and from that, you wish to somehow extract from these analytic information geometric information, which is the geometry of space-time. So to do that, you actually need a bridge that goes from your analysis to your geometry. And the second reason why this is really challenging is because even if there was a linear equation without the nonlinearity, it's almost impossible to write down explicit formulas for solutions of these differential equations, right? Let alone when there's a nonlinear term. So it's never possible to write down an explicit formula for these equations in any reasonable way. However, what you can do is you're able to write down very explicit formula in terms of the underlying geometry of how singularities propagate for that equation. So in particular, for this equation, you know that the singularities of these solutions, or in other words, where these solutions are, say, non-differentiable, always propagates along light rays in your space-time geometry. And because you have these nonlinear terms, when these light rays collide right here, they're actually going to generate another singularity that comes back to where it came from. And therefore, you can actually make observations about these singularities while you're in this space-time cylinder. And so here, we went from these differential equations to using the propagation of singularity to actually understand how light rays propagate. So that is geometric information, right? So we went from our analytic information, which is a solution of differential equations, to propagation of light rays, or trajectory of light rays, which is geometric information. And it turns out that if you know how the light ray propagates in the universe, well, there's a very good chance to be able to reconstruct the space-time of that universe. Right? So that is the idea of how they do this. So they started with a problem that was very difficult, a very difficult analysis problem in differential equations. They turned that into a geometric problem of how light rays propagate through the universe, and they use that idea to reconstruct the geometry. All right? So now, as you can see, you can complain and say, well, this equation is not really realistic because this is rather artificial nonlinearity, right? And that's true. This is just a toy model for a differential equation. And later on, they improved this toy model to an actual Einstein equation modeling gravitational waves. All right, so it turned out that you can reconstruct the space-time geometry if you're able to make machines that propagates gravitational waves, right? So that was their result. All right, so the question is then, well, can we achieve the same thing with less data? Can we measure less data and still obtain the same thing, right? And the reason why we want to do this is because if you really look at from the scale of the universe, Earth is nothing more than a point, right? So here is Earth seen from Saturn, which is only 1.5 light hours away, so that's very, very close in terms of astronomical scales. But nevertheless, Earth is already becoming just the point, and all the orbits and all the satellites is just one point. So really the question is, but now Courant-Laplace and Ullmann require that you observe data on an open set, which is not realistic if you think about it in that picture, right? Because the Earth and its orbit is just a single point. So the question is then, can we, a more realistic model is that if you only make our observation along a single observer, right? So you take a trajectory of a single observer, so that's a single curve, and instead of making observation on the cylinder, you actually only make observations along that curve only. And so that was what I proved, is that you can actually reconstruct the topology and geometry of an ultrastatic Lorentzian manifold. That means your universe is static all the time, your universe never evolves, right? But you can reconstruct that information from simply measuring the solution of this nonlinear wave equation along the trajectory of a single observer. So from a Riemannian geometry perspective, to interpret that into a Riemannian geometry perspective, is that if you look at the solution of the wave equation at a single point on a Riemannian manifold, that is enough to reconstruct the entire topology and geometry of that Riemannian manifold. All right? And of course, our space is not, or our universe is of course not static, so that's not a realistic model. So we then improved, we removed the ultrastatic assumption. Now we're allowed an evolving universe, which is what we live in, right? So again, if you just measure these waves along a single observer, you can reconstruct the space-time and geometry, or the geometry of the space-time for the entire universe.
Even just within a light cone or something, right?
Well, within a light cone, yeah. So everything is modulo speed of light, right? Not the entire universe, but somehow within the speed of light. If you measure for infinite time, of course.
Yeah, sure.
Yeah. All right, so now let's bring ourselves back down to Earth and look at some questions regarding what we can do with seismic waves. Right, so here, let's suppose that you have an earthquake that is happening at the North Pole, right? And the seismic waves will propagate through the middle of the Earth and arrive at various seismic stations around the world. And the information that you get is the amount of time that it takes for the earthquake to travel from its source to the various receivers on the surface of the Earth. And the question is, well, if you know the travel time of these waves to various points on Earth, can we then reconstruct the interior composition of the Earth, right? So this is a typical geophysics kind of question. Right, so now mathematically, this is modeled by something called the boundary rigidity problem, where you have a Riemannian manifold that is unknown. You don't know what the Riemannian manifold is, but you know its boundary. You know the boundary of this Riemannian manifold. And all the information that you're given is the distances between these boundary points, or between pairs of boundary points, which models the time that it travels from for the wave to travel from one point on the boundary to the other. Right. So the question then is that if you know this information about the distance between the boundary points, can you then determine the metric g in the interior up to isometry? And if you can do this, we say that such manifolds are boundary rigid. So this is called a boundary rigidity problem. And the answer is a resounding no. You can of course not do this, right? This is of course not enough information. And I will give you a very simple reason why. Right, so suppose now you have a manifold with a boundary, right? So here's your boundary, and you have a very high metric in the middle, right? So suppose now you want to walk from one side of town, one side of the mountain to the other side of the mountain. You would never try to go through the peak, right? You would always go around the peak, either through the front or through the back, right? So the distances between these 2 points, or any point, 2 points on the boundary, does not record information about the peak, right? You can change the peak however you like, and that would not affect the distances of these shortest curves between boundary points. So this is, of course, the non-uniqueness that you would get, right? And mathematically, this is due to the presence of conjugate points, right? So you can sort of phrase this idea in terms of conjugate points, which is when you have 2 points on a manifold that are joined by 2 distinct geodesics, which are then homotopic to one another, right? So, and this is of course the case in my mountain, because you have 2 geodesics, and then of course this is simply connected, so you can homotope this one over to the other side. So that's what gives you non-uniqueness there. All right, so then Michel conjectured that if you assume that you don't have this nasty conjugate point business, and then you have a convex boundary, and your manifold is actually simply connected, do you then have boundary rigidity, right? So this is the famous Michel conjecture. And so here are 2 manifolds, and you assume that their boundary distances are the same, and then you ask yourself, are they then isometric? Right, so Gromov actually proved this first under the assumption that this manifold is a priori Euclidean. So if you assume one manifold is Euclidean, and then they have the second manifold has the same boundary information, distance information with it, they are isometric. In dimension 2, you can make a slightly stronger assumption, or I shouldn't say slightly, you can make a stronger assumption of non-positive curvature, which guarantees you no conjugate point and more. Right? In that case, Crook and Hotel proved boundary rigidity in dimension 2 in the negative curvature case, or non-positive curvature case. The real breakthrough came because of Pestov and Ullmann, where they actually proved Michel's conjecture in dimension 2. They just needed no conjugate points, and then they were able to show boundary rigidity. And so the proof here is actually quite nice. So I would like to sort of at least discuss some of the ideas there, right? So the idea here is that the first thing they said is, well, the boundary distance information is not really good geometric information because it's just a whole bunch of numbers, and numbers really don't carry too much geometric information anyways. So I would like to consider another information, which is something called the scattering data. So this is where you take a point on the boundary of your manifold and you choose an incoming direction, and you shoot a geodesic along that with that initial point and that initial direction, and then you look at where it exits and the exit direction, and you measure the length of that geodesic. So that is something called the lens data, right? So it takes the incoming point and the incoming direction, and it maps it to the exit point and the exit direction, plus also the length of that geodesic. Right, so that is a far better or more geometric information than just the boundary distance. But it turns out that it's just Gauss's lemma, that from the boundary distance, just a little bit of exercise in Riemannian geometry, you can actually conclude that these two have the same lens data as well. All right, so now this is where things get complicated, and I'm going to skip over this a little. Oh, so right, so this means that you have two manifolds, and then the two different geodesics could take different trajectories for the two different metrics, but nevertheless, their incoming direction, their outgoing direction could be the same. In the middle, they could do crazy things. They could be different. Right? And so this is where it sort of takes a leap of faith, is that because they concluded that because your geodesics behave the same way in the sense that they come in and go out, your harmonic functions must also behave the same way. They have the same boundary behavior for the harmonic functions. Because you think about it, sort of the normal derivative of a harmonic function is kind of like an outgoing direction, and then where the value of the harmonic function is kind of like the initial point, right? So that's kind of waving my hands a little bit. Right, and from that information, of course, by a result of Lassens and Ullmann, which says that if you have the same boundary information for your harmonic functions, then the two metrics belong to the same conformal class. All right, and once you have that they're in the same conformal class and you have the same boundary distance, it's a volume calculation to show that the conformal factor is actually just 1, and you really have isometry there. All right, so you can actually, so one result that I should have put on the slide is our mutual friend Colin Guillermo. He was able to remove the simply connectedness assumption. So he's allowed these manifolds to be trapped, right? So he's allowed to have genuses. Geodesics could become trapped, and that was a major breakthrough as well. All right, so now after they had this breakthrough, is that there was a contest now to actually see how many of these assumptions that we can remove, right? So the first thing that got removed was this no conjugate point condition by Stefanov, Ullmann, and Bassi in dimension 3 and higher. But in order to remove that no conjugate point assumption, they need to pay a higher price on the convexity, right? So they not only require the manifolds to be convex, they needed to have a convex foliation. So roughly speaking, that means that your manifold is like an onion that has layers that you can peel off, right? So so that's the way to think about it, and that's actually how the proof went. Right, so they needed a convex foliation. Now, if you remove the convexity result, Guillermo Mazzucchelli and I had the result where we didn't need the convexity, but we needed no conjugate points. Right? And the difficulty there is that the shortest distance between 2 points on the boundary is no longer a geodesic, right? So here you have a non-convex manifold, and the geodesic, well, it gets out of the manifold, so you're not allowed to consider this curve anymore. So the shortest distance between x and y is obtained by, well, going along geodesics first, wrap yourself around the boundary, and then go along geodesic again, right? So you're not working with geodesics anymore. That makes things a little bit more tricky. Another thing that makes it tricky is, remember this lens data where you have the incoming direction and you see where this thing exits? Well, this thing is going to be discontinuous, right? So you start shooting geodesics from this point y, and as you vary the angle, well, all of a sudden you vary your angle a little bit, it's going to start shooting a lot longer, and then so you're dealing with a discontinuous lens data. And that actually creates technical difficulties that we dealt with. All right, so now let's bring down to the quantum mechanical level on a very sort of subatomic level, talk about some quantum mechanical effects. All right, so before I talk about this, I would like to give everybody a reminder on how magnets work, right? So as you can see, there's a magnet and there's some magnetic fields, right? And we learned in our undergraduate magnetism class, I think for me, was that your magnetic field, or the things that you see here are always given by the curl of a vector potential, right? And A is called a magnetic vector potential, and E is called a magnetic vector field, right? So classically, only the field matters and the potential doesn't matter at all, right? So this is what you were taught in your electromagnetism class. So, and the second thing that you should remember is that a magnetic field always exerts a force on a moving charge, right? So here is a electron that is going across that way, and there is no field, so it just keeps on going straight, obviously, right? However, if you were to turn on the magnetic field, right, it's going to start to bend that electron, right? So the bigger the field, the more that electron bends it as it shoots forward, right? So this is two things that you should remember from your electromagnetism class, is that only the electric field matters and not its magnetic potential, and also that magnetic field exerts a force on a moving electron. All right, so now remember these double slit experiments that we all heard about, or most of us heard about in our physics class, right? This is where you shoot a bunch of electrons through a double slit, right? And you look at what the distribution of these electrons is when they hit that detector, right? So of course you get a nice even distribution, right? So now, the experiment of Iron Hot Bomb, what they did was they placed a solenoid behind that double slit, right? And they had a magnetic potential, which is not zero, but its field is zero both inside the solenoid and outside of the solenoid. So there was really no field anywhere. And they performed the double slit experiment. So they shot a whole bunch of electrons, and then, not surprisingly, because there was no field, so nothing really acted on these electrons in the first place, so you again get a symmetric distribution of where the electron hits that string. What is weird now, what happens, is that what they did next was that they set up this experiment. Did I press the right? So sorry. They set up this experiment in such a way that they had a non-vanishing non-vanishing magnetic potential, where the field is zero on the outside, but the field is not zero on the inside that solenoid. But the electron never passes through that solenoid anyway. So the electron never passes through any area that had any magnetic potential, magnetic field, because all the magnetic field is hidden in this solenoid right here. So what you expect is that because the electrons never went through any magnetic field, it should give you the same symmetric distribution again. But that was not the case. What they end up getting in this experiment was a very skewed distribution of where your electron hits the string. So it turned out that when you had no field, electrons got bent anyway. So what happened here, right? So yeah, because the electron never passed through any magnetic field, so this doesn't make any sense. So is there a geometric explanation for this effect, right? This so-called Aharonov-Bohm effect. So in the Euclidean setting, by Estedo and Wieder, they did something so they partially answered this question in the Euclidean setting. But what I really wanted was a geometric understanding of what is going on using geometric wave propagation. So the experiment, or the thought experiment that we set up, was this. You take a Riemann surface, right? A compact Riemann surface with boundary, and then each boundary you glue on Euclidean ends, right? So you just glue on these complex planes at the end of a compact Riemann surface. And what you do is you place a magnetic potential A on this Riemann surface, and you send a plane wave through, right? So this plane wave will propagate, and it will interact with that potential, and it will scatter to produce these eddies. And these eddies will then propagate back out to infinity to give you a wave profile at infinity, right? So these waves are described something by a differential equation of this form. So you take d plus ia star, d plus ia u is equal to lambda squared u. So this will be an eigenvalue problem. And so what you're interested in is the profile of these solutions near infinity at the ends of these, at the infinity of these complex planes. So what we proved was that two magnetic potentials, A1 and A2, have the same scattering profile at infinity, if and only if they have the same field, of course, right? Because field is what matters. But also, you also need the fact that the integral of A1 minus A2 along any fundamental group, or any element of the fundamental group, is an integer multiple of 2 pi. Right, so that is the, and so a corollary of this is the Aharonov-Bohm effect, is that a magnetic potential A is invisible to these wave scattering, so a wave which has passed through this magnetic potential as if nothing, as it was not there, if and only if it has no field. That's not surprising, right? So you, of course, if there's a field, it will affect the electrons, but also you need that the integral of A along any closed loop is an integer multiple of 2 pi, right? So why? Why is there's this weird condition of an integral being an integer in this otherwise continuous differential equation problem, right? And the mystery turns out to lie in this operator d plus IA here. Right, so let's look at this from the perspective of connection geometry. Right, so let's just look at the most trivial bundle, which is E, which is the trivial bundle, the trivial line bundle on the Riemann surface. So essentially, you can think about it as at every point on a Riemann surface, you slap on a complex plane, and you look at this d plus IA guy as something called a connection. So that's simply a way of differentiating sections on this bundle. And you take a closed loop, and you look at a point z naught on that closed loop, and you fix a vector v, initial vector v, over the point z naught of this bundle, and you parallel transport this guy using your connection map law. Right, so it's going to get parallel transported, and then it's going to come back to the same point to be a different vector because there's some curvature there. So you're after you parallel transport, you become a different vector when you come back to that same point. And it'd be nice to be able to write down what the resulting vector v prime is in terms of the initial vector you started with v. And that is actually not too hard to do. Right? So the vector that you obtain via parallel transportation is nothing more than the original vector that you started with times e to the I integral of over gamma over this closed loop of your one form A. And so notice that this parallel transport gives you the identity map, or v prime is equal to v, if and only if the integral of this one form A is an integer multiple of 2 pi, right? Because e to the integer multiple of 2 pi is 1. Right, so this is where this condition comes from. So this connection is invisible to parallel transport, if and only if the integral of A along closed loops is a multiple integer multiple of 2 pi. And these are actually, they have a name for these connections. They're called ghosts because you don't see them via parallel transportation. All right, so finally, the last story that I'm going to, how much time do I have?
About 20 minutes.
I got 20 more minutes? Great. All right, so the last story that I'm going to tell you is about medical imaging. This is where how you can use these waves to actually see what is inside your body. And there are two things that I can tell you about. This one is called impedance tomography, and the other one is called X-ray or geodesic X-ray tomography. All right, so let's talk about impedance tomography first. So this is where, suppose you have an object of unknown conductivity, gamma, and you wish to find out what the conductivity is without breaking this object apart or drilling holes or taking out samples. So you want a non-destructive way of measuring what the conductivity is. So what you do is you place a surface voltage on this object, and the surface voltage will induce an internal voltage, which then will induce a surface current flux, which you can then measure. Right? So the data that you obtain is the input voltage, and then the output current corresponding to that input surface voltage. So the question is, from this set of data, if you do this experiment many, many times, can you then determine what the conductivity is? Right, so mathematically, this is given by something called the Calderon problem, where you are given the boundary information of all the solutions of this equation Laplace plus VU is equal to 0, and you ask yourself from this set of information, can I then determine what that coefficient V is? So there's also this partial data problem, where you're trying to determine the same thing by only making the measurements on only a part of the boundary. So this part of the boundary you do not have information on. And this is realistic because very often you cannot make medical or measurements on all of the patient. You can only get one side of the patient. So Sylvester and Uman in 1987 obtained the result for the full data. So they showed that if you have the boundary information of all the solutions of Laplace plus VU is equal to 0, you can then recover what the coefficient V is. And it turned out that you don't really need the full data. Koenig, Schuster, and Uman in 2007 showed that you only need to make this measurement on a small part of the boundary, at least in dimension 3 or higher. Dimension 2, we were stuck on it for a while until Bukin came along in 2008, which is relatively recent in mathematical terms. And then using some of the ideas there, Emanuele, Yamamoto, and Uman show that, again, in 2 dimensions, you don't need the measurements of all of the boundary, you just need part of the boundary measurements. And because there are quite a bit of harmonic analysts here, I would like to talk about these partial data problems and how they might relate to some problems which are about that are very classical in your field, which is the unique continuation problem for elliptic PDE. Right, so I'll tell you what these problems, I'll explain for you what these problems are in case you haven't seen it before. Right, this is where you have a solution to the differential equation Laplace plus VU is equal to 0, and you assume that on a small part of the boundary that U is equal to 0, and its normal derivative is also equal to 0. And then you ask yourself, well, does this set of information uniquely determine the fact that U is identically 0, right? So is this the only allowable solution once you had made the assumption that Laplace plus VU is equal to 0, and its boundary and its normal derivative is also 0 on a small part of the boundary? And you can see that this problem is somehow related to this one in a philosophical way, right? So here you have a fixed V, and then you have a solution U that you only know part of the boundary for, or the part of the boundary behavior of the solution. You're trying to uniquely determine what the solution is. Here you know part of the solution, part of the boundary behavior of all solutions, and you're trying to determine what V is. So in the sense that these 2 problems are dual to each other, the yin and yang of each other, right? And so what can be done for unique continuation for elliptic PDE? Well, it turns out that you do have something called a unique continuation. This is back in the days by Karl Mann in 1939. He showed that, at least in dimension 2, Laplace plus V has unique continuation property when V is in L infinity. And then, after he proved this, there started to be a contest on how you can make this infinity lower. And so one person who made some contribution to this was Hermander. He showed that when n is less than 4, this operator Laplace plus V has unique continuation property when V is just L2. Right? So that's a significant improvement from what Karl Mann did. However, the real winner to this contest was Jerson and Koenig in 1984. They showed that for n greater than or equal to 3, Laplace plus V has unique continuation property when V is just in ln over 2. Right? And then furthermore, they showed that this is optimal. Once you get below this, you start getting counterexamples. All right, so this is sharp. So now the thing is that if we really believe that these partial data impedance tomography problems are the dual to these unique continuation problems, we really ought to be able to improve from L infinity to something that is less integrable than L infinity. And that is indeed what we did, right? Chung and I showed, and my current student Bush and I recently, showed that in various settings, all you need is V to be in ln over 2, which is exactly the same coefficient as Jerson and Koenig for their unique continuation problem, to solve the partial data inverse problem, right? And a nice little story here is that Chung is actually the PhD student of Koenig. right? So it's kind of a nice circle of people working on these problems. All right, so now there's no reason why we must consider Calderon problem only on Euclidean domain. We could definitely change that Laplacian to a metric Laplacian on any Riemannian manifold and ask ourselves the same question. If we know the solution to the Laplace plus bu is equal to 0, on the boundary, or all the boundary behavior of these solutions, can we then determine that coefficient? So in dimension greater than or equal to 3, the result here is by Koenig, Salo, Ferrer, and Ullmann. They needed some very stringent assumptions on what the Riemannian manifold is. So the Riemannian manifold needs to be a Cartesian product of codimension 1 submanifold, which is m prime, and the real line. And furthermore, it also needs to be a metric product. So your metric needs to have a structure of 1 and g prime, right? So really, it's honestly a geometric cylinder that they're considering, right? So they can also they can also deal with conformal classes of these, but topologically, that's what you're stuck with. Dimension 2, any Riemann surface, right? You can have any topology you like, any geometry, whatever. So Riemann surfaces are much easier to deal with, right? And also, furthermore, we only need a partial data measurement. You just need this. These data on a very small part of the boundary. All right, so last story that I will tell. How much time do I have again?
10 minutes.
10 minutes? Yeah, okay. So last problem is this geodesic. So we all know what CT scan looks like, right? So here's a patient, and you have a scanner that emits. Keep on running away from me, but this thing shoots out X-ray, and then there are detectors on the other side that measures the X-ray attenuation as it goes through your body, right? So then the question is, so mathematically, this is modeled by if you have a compact manifold with boundary, and you have an unknown function f, which is piecewise continuous, right? So in this case, you just take the function, support of that function here. And for each geodesic L, you measure the integral of this function f along that geodesic. And then you do this for all geodesics emanating from that point. And then you actually do this from every single point on the boundary. So the data that you get is IF, which maps L, which is an element of the space of all geodesics, to the integral of f along that geodesic. Right, so here's so IF is a function on the space of all geodesics. So if you haven't seen this before, this is what it honestly looks like, right? So here is a brain, and that is actually the raw data that you get from measuring the attenuation of X-ray as it goes through the brain. So the horizontal axis parameterizes where the source is placed, and the vertical axis is the angle of that source. So the question is then, can we go from the raw data that's given to us by the CT scan to the actual image of the brain, right? And if we can do that, what is a systematic way of doing this image reconstruction? Well, it turns out that that is not the question that I'm really interested in. See, because if you really want to care, all you care about is whether or not this patient has a tumor. Well, the tumor is pretty easy to spot if you can just say that there's an interface there. There's a jump discontinuity between normal brain tissue and abnormal brain tissue, right? So really what you're not trying to determine is what is F, but rather what is the interface of F, or in microlocal analysis parlance, we say the wavefront of the function F, right? So this is where wavefront roughly measures where the function is singular, or where it jumps, and also the direction of these jumps. All right, so here you can see that here's a patient with a tumor, and then the CT scan actually shows that there's this little band here that corresponds to that tumor. If you see, this is particularly wider than the rest, and that's actually corresponds to the fact that there is this jump right here. All right, so Now, I'll give you a mathematical intuition as to why we can detect these interfaces using just these integrals along geodesics, right? So here's a function with the interface. Here's a function with f is equal to 0, here f is equal to 1 here, and here are your interfaces, right? And if you look at these geodesics, so you measure the integral of f along that geodesic, which is of course equal to 0. The integral along that geodesic is also 0. That is also 0. But whoa, here you actually hit something in, you hit f along your integral, right? So you're integrating out to be something that is 1. So even if you don't know what's going on inside, right, so you don't get to see this, but all you need to do is look at this set of numbers, and you go 0, 0, 0, and 1, so you know that this last curve must have hit something, right? So you know that the guess is that the edge of the support of f must have gone along that geodesic. And this guess fits somewhat with the upper interface of that region, right? So that is the intuition behind being able to detect these interfaces using X-ray tomography. And so it turns out that using micro-local analysis, or the intuition is that the jumps in measurement correspond to jumping your function f, or the wavefront set of your IF corresponds to the wavefront set of f. So it turns out the theory of Fourier operators, which is developed by Deichler and Hohmander, gives you a systematic way of doing this, right? So there exists a map phi mapping the cotangent bundle of the manifold of all geodesic trajectories to the cotangent bundle of your manifold. The graph of this phi is actually a Lagrangian submanifold, so this is a symplectic map, such that you take the wavefront set of your X-ray attenuation, or the raw data from your CT scan, you map it by this phi, and then you get the jump interface of your brain tissue, right? So that's like the theory of the Fourier operators. So the map phi can be constructed if we know the trajectory of these geodesics, right? So there's a systematic way of writing down what this phi is, using if you know what the trajectory of these geodesics. So what we did with Mazzucchelli and Salo is that we had a method for locating the jumps of f from your IF, and we can also detect these ramps. We can also detect any CK singularity, right? So these are actually not so surprising. All these are within the framework of classical framework of Dijksterman and Hohmander. What is new is that we are actually able to detect analytic singularities from f to IF, and this is not within the framework of Dijksterman and Hohmander. So Dijkster and Hohmander, their theory does not apply in the analytic category, and we're able to develop a theory that's able to deal with the analytic category case. All right, so once you're able to get analytic singularity, you can actually show honest injectivity results. So you can show that if IF is equal to 0, F is equal to 0 by some kind of analytic continuation technique. We call it or micro-local inference theory. All right, so now another thing is that our framework applies to a broader scope of settings, right? So we can deal with geodesic X-ray transforms, we can deal with light ray transforms, and which we can also deal with integrals, and not just along curves, but integral along hypersurfaces. So you have a foliation of hypersurfaces, and you're integrating, you know the integral of a function along all these things, all these hypersurfaces, you can actually reconstruct the function. So previously, all these were dealt with using an ad hoc techniques of various authors. Our theory actually just gave a unified structure to just everything, and just everything just falls in within within the scope of our theorem, right? So we turn that into a unifying principle. How much longer do I have?
2 minutes.
2 minutes, perfect. Actually, in 2 minutes I can talk about data science. All right, so now here so far is that I have my measurement data for all geodesics, and if I know what the geodesic look like, I can have the dictionary, which is the symplectomorphism, which then maps to the geometry of the interface of the function that I wish to recover. So what if we do not have knowledge of the geodesic trajectory, which is the true thing, right? Because you don't really know what the inside of the brain looks like, so there's no way how you should know how X-ray propagates in your brain, right? Then you don't actually get your symplectomorphism. So how do we then get our hands on the wave or the interfaces of these brain scans? Right. The solution here is actually to learn that dictionary using machine learning. Right. So here you actually need a whole bunch of training data. So suppose you have training data wavefront of your sample F1, and you measure. You make these measurements, and then you get the wavefront set of IF1, and you take another F2, and then you look at its wavefront, and you take all these measurements, and so on and so forth. So you get a whole bunch of training data. And then now you just use the fact that you have a whole bunch of training data to plug that into machine learning to actually not to learn the image, but to learn the symplectomorphism right there, right? So and furthermore, you can use the fact that that graph is a Lagrangian submanifold, which actually gives you an extra condition, and that would actually, we're hoping that it would actually make your learning faster. All right, so this is related to a submanifold reconstruction algorithm by Fefferman and Tel, which came out in 2015. All right, so the advantage to our approach is that our AI is based on Gurmander's theory versus just the black box AI. So if one day I ever need to have a brain scan, I would rely on Gurmander much more than I would rely on a black box, right? So, and this also gives a direct X-ray transform data to edge reconstruction. So right now what we need to do is you take your raw data, you actually need to reconstruct the image, and you need to feed that image through an image processing algorithm to actually show you what the interfaces are. Our method cuts out the middleman and just goes directly to your interface reconstruction, right? And that is all that I have. Oh, right, just the advertisement. So what I just told you was somehow you can use machine learning to solve a dynamical systems problem, right? And then of course there's the other way around, is that how you can use a dynamical system to solve a machine learning problem, and that is going to be at 3 p.m. Right, and that is the end of my talk. Oh, no, that's next week, but still.
Okay, and lastly, did you have any questions or comments?
As a patient, do you have a right to request your data if you get a brain scan?
I would,
And
I
you would insist on it?
I was just telling people that I had a root canal and they had to get the X-ray. I thought about asking for it, but they did not use a CT scan in that case. It was just an X-ray. But yeah, that would be really cool to be able to get yourself the raw data.
Yeah. I don't know what they would say to that.
Yeah, I would like to. Yeah, I would like to see that.
Yeah.
So when you say like partial data, like how partial? Like what do you mean by partial?
Partial. It's well, it's kind of like when you don't get the measurements on the entire patient, right? So if you want to say like do a lung image your lung, right? You can only have detectors at the back, I believe, right? Because at the front there's too much stuff that needs to go through. You can't get data from having detectors at the front.
Right, but so as far as like the theorem goes, you said you could construct using partial data, right?
Yeah.
How little?
How little? Well, that depends. So dimension 2 is any small open set on the boundary. You just measure your normal derivative of your harmonic function through there, and that's enough. In dimension 3 and higher, what you need to do is, can I use this board? Yes. So what you need to do is you need to take, so suppose now your domain is convex, right? And you take a flashlight, yeah, and you shine a light on it, right? And you need to be able to measure that in your illuminated region.
Any point outside?
So you're not allowed. So you have no measurements outside of your illuminated region.
No, I mean the point when you set the
At
line.
any point outside. So
Any point outside.
in a non-convex set, you take the convex hull of this, and you take a point outside of that convex hull,
Yep.
and you shine a light, and where the light shines, you make measurements on there, and that's your partial data. So in the convex case, of course, you can bring this light as close as you like, and you're only illuminating a very small part. Right. But the difference here is that you need Dirichlet data on everything, and then you measure Neumann data in this very small part in dimension 3 and higher. In dimension 2, you just need Neumann and Dirichlet data in any arbitrary small set is enough. So dimension 2 is more, you have stronger results. Far stronger results in dimension 2.
But actually, yeah, we need some conditions on the boundary, right?
No, like I said, suppose you have a convex thing, then it works out nicely.
Yep.
But if you don't have a convex thing, then you take a point outside of the convex hull, and then you shine a light, and then but then it's not as clean. It's not as clean
I
as
see.
a result as you can say.
Do you
Stick
need
here.
any regularity though? Like,
Oh, of course, yeah. So right. So I tend to live in the smooth world.
probably.
Like I think
Lipschitz.
Lipschitz. You want at the end of the day, you do want your elliptic problem to be well posed.
Yeah.
Right, so
Maybe
you-
if you can solve uniquely the Laplacian with Dirichlet, then that's enough or something like this.
Right. I mean, you want well posed, so you don't want like Lebesgue spline things like that. Cusps.
Yeah.
Try to avoid that.
Yeah. Do you know what's the optimal transport sort of approach? These kind of problems seem like they would be
Optimal transport.
would lend themselves well to an optimal transport kind of approach.
Which one of the problems?
I don't know, a lot of them actually. They sort of remind me of some things that kind of Villani and Figali would do.
So that is becoming part of the machine learning algorithm.
Yeah.
Right. So you when you're doing machine learning, there is a cost function that you're trying to get optimize, and then very often you want to interpret your data, especially if it's positive data. Is in our case, that you interpret your data as probability measures.
Yeah.
And then, of course, there is this sort of this Wasserstein metric that's on probability measures, which optimal transport uses, right? And then that's the cost that they use, the Wasserstein metric.
Yeah. Still, I don't know. Yeah, I just wondered about some of the.
So that is being used in inverse problems. That aspect of it.
Yeah.
So you mentioned
The hoop is the name, the reference. The hoop. Yeah. So he uses that. If you want to check that. Yeah. Sorry.
you mentioned Fourier integral operators, right?
Yeah.
What kind of role they can play here technically? This kind of like, and can you avoid them? Because you kind of suggested that actually at the end of the day you can kind of avoid the techniques, right? You said that Hormander and so on is kind of no longer of use.
No. I say I'm using Hormander. I'm incorporating Hormander and Dijkstraat
Okay.
into machine learning algorithm. But of course, if you use a black box approach, then of course you don't need any mathematics at all, right? So I think traditional machine learning, you just take sets of data and then you fit them the best possible. But that's of course don't let the data science people say that I just said that. But that's roughly what they do. But if you want to incorporate the Hormander machinery, right? So you want to learn your canonical relation instead of learning just the input and output. Right? You want to learn a very specific thing about your FIO, which is the canonical relation. And because you know that your canonical relation is a Lagrangian submanifold, that actually gives you extra restriction, right? And extra information. So you may not need as much data.
So you look at for propagation of singularities, or you?
Yeah.
Okay.
Right, so essentially the problem for reconstructing wavefront is the propagation of singularity. You're trying to prove an elliptic regularity result for an elliptic FIO. Right, and that of course depends on your canonical relation because it takes your wavefront from your input to your output and you want to go backwards.
And one question about the nonlinear PDs. I mean the way
The first one,
equations.
yeah, the way-
yeah, right. And I remember that like for the case of Rn and the nonlinear PDs, they were studied quite well, right? And I remember that like we have like the time derivative and then the Laplacians acting on U and then plus like due to the power alpha or something like that, and then they have some, I mean, some case of alpha like maybe between -1 and 1 or something like that. And what is the main difficulties for your setting?
What is what?
I mean, the main difficulties in your setting in comparison with like the Laplacian case.
So here's the thing. The harder your forward problem is, which is what you were telling me,
Yep,
the easier your inverse problem is.
yep,
Right, because what makes forward problem hard is that you have very rich behavior for your solutions. And in inverse problems, you do want rich behavior in your solutions because
Yeah, right.
the more structure you have on your solutions, the more you can extract about your differential equation. Right?
Yep.
So what makes nonlinear equation hard in a forward problem is what makes it easy.
yeah, right.
And so I wonder how quickly I can go back to slide 1 by just clicking on this. Aha, so clever. So you can see here, right here. Right. So if this nonlinear term wasn't here, these propagations would just simply propagate, and they would not interact and give a echo coming back, right? They would just propagate out. This red curve would continue, and this blue curve would not exist. And so if you're an observer in here, you see nothing. And when you see nothing, that's a very hard inverse problem to solve, right? And the only reason why you have any hope is because you have a nonlinearity that gives you that interaction, and it propagates singularity coming back. And that was the major sort of observation of Krylov, Lassas, and Ullmann, is that nonlinearity and inverse problems, they help you, rather than make your life miserable, like in the forward problem case. I know that I don't know forward problem very well in this case, like all the literature on it, but I know that you can construct some very, very strange solutions, that it has singular support almost everywhere, something like that.
Okay, if we do not have any questions, and let's thank you again.
Hey Justin, can you stop recording?